Lesson 3.2, Function Notation and Graphs. First, we need to understand functions. We already discussed that functions are used to represent relationships between two values. One value will be dependent upon the other. The independent value is called the independent variable. If we use x and y is generally dependent and x is generally independent. That means we can pick any number for x, we plug it in and we get y. Every x value can only have one y value. So if we plug in x, we can't get two different y's out. We can only get one y out. The independent values make up the domain, so all of the x's are the domain. The dependent values make up the range, so all of the y's are the range. And it can be written without two variables using function notation. For example, I can write y equals 3x minus 5 as f parentheses x equals 3x minus 5, and I'll tell you how to read that momentarily. Other letters can be used as well. We can use f, g, or h, etc. If we want to evaluate functions given function notation, first we know that they can be written in a form called function notation, and that's what we have here. And it's read as f of x. So when you see this parenthesis set up, that's f of x equals 6x minus 7, or you can say 6x minus 7 is a function of x. You can only use this notation if you are actually a function. So once you see that, you'll know it's a function. You don't have to do any of the tests. We can evaluate the function for various values of x, which was similar to evaluating expressions when you were given the value of the variables. So for example, we said evaluate 6x minus 7 for x equals 3. But if we're doing it in function notation, we write f of x is equal to 6x minus 7, find f of 3. In both cases, what we'll do is we'll plug in 3, and we'll get 18 minus 7, and we will get 11. So f of 3 will equal 11. Okay, so here we have some functions to evaluate. We have f of x is negative 11x plus 6, and g of x is 3x squared minus 10. So we want to find f of 6. F of 6 is going to equal f of x with a 6 plugged in. So we'll take the x out and put the 6 in. So we will get negative 66 plus 6, which will give us negative 60. So f of 6 is equal to negative 60. G of negative 3, we will take g of x, and to evaluate for g of negative 3, we plug in the negative 3. Negative 3 squared is 9. So we get 27 minus 10, which gives us 17. So g of negative 3 is equal to 17. We can go backwards. If we know f of x is 10, and we know f of x is 3x minus 5, we can find the value of x. So f of x is equal to f of x. So I take that 3x minus 5 and I set it equal to 10. And then we solve that equation. 3x is equal to 15. Divide by 3. And we have x is equal to 5. We can find another value of x if f of x is 2 times the absolute value of 2x plus 4 minus 6, and f of x is 14, I can set those two things together and then solve for x. First, we'll add 6 to both sides, giving me 2 times the absolute value of 2x plus 4 is equal to 20. Divide by 2, giving me the absolute value of 2x plus 4 is equal to 10. Now remember, with absolute value, this in here could be 10 or negative 10. So we have to solve for both. So we split this equation and we solve 2x plus 4 equals 10 and 2x plus 4 equals negative 10. Subtract 4 from both sides, 2x equals 6, divide by 2, x equals 3. Subtract 4 from both sides, 2x equals negative 14, divide by 2, x equals negative 7. So we get an answer of x equals 3 or negative 7, and this is okay. Two different x's can give us the same y. We just cannot have one x give us two different y's. Let's look at an example of a function we can graph. We have that when Jacob digs, the Earth's temperature rises the deeper he goes. He digs 5 meters down, and the temperature is 8 degrees Celsius. For every 5 meters, the temperature rises a constant 8 degrees Celsius. If the temperature continues to rise, we determine the function that represents this relationship and we graph it. Right now, we're just going to worry about graphing it. So we're going to set up a data table. We'll have x and y, where x is equal to the depth of the hole, and y is equal to the temperature. Okay, so we know that at 5 meters, it's at 8 degrees Celsius. And then when he goes 5 more meters, so we're at 10 meters, we're another 8 degrees Celsius, so that would be 16 degrees Celsius. At 15 meters, we're another 8, so that would be 24 degrees Celsius. At 20 meters, another 8, and then at 25 meters, another 8. So now we want to graph this function. The depth of the hole is our dependent variable, our independent variable, because that is the thing that we have control over. And the temperature is the independent variable because the temperature depends on how deep the hole is. So this is hole depth, and this is temp in degrees Celsius. So I have 8, 16, 24, 32, 40, 48, etc. And then for hole depth, 5, 10, 15, 20, 25, 30. When we were at 5 meters, we were at 8 degrees. When we were at 10 meters, we were at 16 degrees. When we were at 15 meters, we were at 24 degrees. When we were at 20 meters, we were at 25 degrees. And when we were at 30 meters, well, we didn't go that far, but 5, 10, 15, 25, we're at 40 degrees. So each of these dots represents the coordinates 5, 8, 10, 16, 15, 24, 20, 32, and 25, 40. Now that we've graphed some functions, we need to learn how to interpret graphs. In addition to determining the value of x from an equation in function notation, we can also determine values from a graph even when we don't know the equation. So for example, I want to find f of x when x equals 3, or find x when f of x equals 0. What I do is I look at the graph and I find x is 3, and I come up and here's f of x. So 10. And I can find x when f of x equals 0, f of x equals 0 when y equals 0, and y equals 0 here and here. So x would equal -2 or 1. Why don't you try this one? Find f of x when x is 1.5, and find x when f of x is, 5. Pause the video, figure it out, and then when you're done, we'll start back up and we can compare answers. Okay, how did you do? The reason I determined 3.8 is due to the number of spaces between the numbers. I was able to determine that each space would be about 0.2, and we have 0.2, 0.4, 0.6, 0.8 right here, so 3.8. When f of x is 5, I came across here and then went down to find that x was 2. But what do these results tell us? Well, right here we have total price, and down here we have pounds of carrots bought. This tells us how much it's going to cost us, depending on how many pounds of carrots we buy. Finally, we'll discuss some sequences. A sequence is a series of numbers that follow a specific pattern. We can have the pattern be anything at all, but in order to be a function, every input value can only have one output value. Sometimes a sequence can be easy to determine. 2, 4, 6, 8, 10, 12, 14. We're going up by 2 every time. 10, 15, 20, 25, 30, going up by 5 every time. Sometimes it's a little harder. 3, 7, 15, 31, 63, 127. Now we have to think about this one for a little bit. Okay, so here we know that we're going up by 2 every time, and here we know we're going up by 4 every time. Or sorry, 5. So look at this. We go up by 4, and then between a 7 and a 15, we go up by 8, and between a 15 and a 31, we go up by 16, plus 32, plus 64. So that one required a little bit more thought. And then this is actually a very famous sequence. This is the Fibonacci sequence. And I'm so sorry if I'm not spelling Fibonacci correctly. We go up by none. Then we go up by 1. Then we go up by 1 again. And then we go up by 2. And then we go up by 3. And then we go up by 5. And then we go up by 8. And wait a second. 1, 1, 2, 3, 5, 8. 1, 1, 2, 3, 5, 8. The Fibonacci sequence is very famous, and the way it was determined was that every number is the sum of the two numbers before. So 2 is the sum of 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3. 8 is 3 plus 5. 13 is 5 plus 8, etc. There are specific formulas that can be used to determine sequences. We can have an explicit formula, which can be used to generate any term in a sequence if we know the number of the term we are looking for. So the first or the 10th or the 15th number in the list. So if we're given this sequence, 1, 3, 9, 27, 81. To get from 1 to 3, I can either add 2 or I can multiply by 3. To get from a 3 to a 9, I can either add 6 or I can multiply by 3. To get from a 9 to a 27, I can add 18 or I can multiply by 3. So we can generate this explicit formula and we can say, okay, our first term is a 1. If we multiply that by 3, we get 3. If we multiply that by 3, we get 9. If we multiply that by 3, we get 27. Okay, so now we have to figure out a formula that will do this. So we start thinking, okay, basically I'm multiplying by 3 every time. But if I say x is 1, multiplying by 3 wouldn't really work. But what I could do is I could say 3 to the x and have our first term be 0, and 3 to the 0 gives me 1, and 3 to the first gives me 3, and 3 squared gives me 9, and 3 to the third gives me 27, etc. So my explicit formula would be 3 to the x. Now we have something called recursive formula. Recursive formulas can be used to generate any term in a sequence if we know the previous term. The new term is in relation to the previous one. So if we have this formula that we've been given, so f of n is equal to f of 1 plus f of n minus 1. And we know that f of 1 equals 8. We can use this to find f of 7. So f of 1 is 8. F of 2 would be f of 1 plus f of 2 minus 1. So it would be f of 1 plus f of 1, which would give me 8 plus 8, which will give me 16. F of 3 is going to be f of 1 plus f of 3 minus 1, so that's f of 1 plus f of 2, which is going to give me 8 plus 16, which is 24. F of 4 will be f of 1 plus f of 4 minus 1, which is f of 3, so that's 24. So 8 plus 24 will be 32. F of 5 will be 8 plus 32, which will be 40. F of 6 will be 8 plus 40, so that will be 48. And f of 7 will be 8 plus 48, which will give us 56.